Hey, Nick. Welcome. So it's like this is the intermission before the stream starts. Alright, I think that's enough time. 3 minutes. So, what did I do last time? Let's find out. Let's find out right now. Spider, good morning, evening, whatever. It's morning where I am. It's, what time is it? You see this? 10:13. I have a picture of my, mobile GitHub as my screen. It's the front page of my phone. It would have been black otherwise. Anyway, it's early where you are, late where I am. So, wait, did I push everything? Did I pull? Pull, get push. Okay. So, I implemented basically all of this today. Did like 10 commits today. Today was my most productive day. I've never been more productive since the start of the school holidays, which was a month ago when I started working on this programming language. So, hash 17, stream 17. This is a type aliases, some types, and struct initialization. So we did that last stream. And in between then and now, incremental makefile. Okay, this is just, if you thought GCC with all the files was quick, this is even quicker. Let's go make clean it all, and then just make. Okay, that wasn't much faster. But let me just save a file, run it. Wow, isn't that quick? Isn't that so quick? Yeah. It's just nice. Quality of life, right? And I also have this thing here, so when I'm working on my laptop, because Debian ships a extremely old version of GCC that doesn't even compile my code, so I have to use Clang. But other than that, I try to use GCC. So incremental makefile, that's one of them. Next thing, so I started a unified implementation of UFCS, Unified Function Call Syntax Method Calls. And what I was talking about last stream, I think I was talking to spydr about how in this compiler I have two different worlds. One is my type table, and another one is my type symbols. Those are two separate things. And let's say you have the structs stored here and the type symbol stored here. You have to I merge them together in one go. CI, hey, welcome back. Do I get a haircut? Yeah. Like a week ago. I got a haircut a week ago because I go to a school that requires it. Yeah. I like having really long hair. Okay, so after that, I unified the two type type system worlds together, and I'll quickly show that off. In here. So there is no type symbol T. So here, this is basically the type symbol T, and this is what's stored on a symbol. So you have a union. This is your symbol T, and you have a union of dproc, dglobal, and dtype. So this is the type symbol. There's no storing of structs or anything. All it is just a pair of type T, and just some debug information. So it just stores the locations, field lock and type lock. So all it is just type symbol, type to type. So if you declare, let's go right here. Let's go like struct T equals struct T equals whatever, right? This is basically syntax sugar for type T equals struct anonymous struct. So whatever I was talking about to spydr last stream, I essentially implemented that. So now structs are anonymous. They aren't. They don't have this sort of like there's no two different worlds. So it simplifies things. It makes things easier, which is exactly what I want. Okay. All right, what's next? Yeah, method calls. Yeah, so finish unified method calls, address a fucking field access. Eager struct literal parsing. Okay, so this I was in I was inserting timestamps for the last VOD, and I found that the parts where in normal in the reordering, where I basically checked the sanity of struct literals, that was like I don't know 20 minutes long and so much code, but basically I have I can do this instead. Eager struct literal parsing, and what it does is essentially instead of having if I can go to here. Here you go. Instead of having, let's say you have essentially, you can think of a struct initialization as an infix operator. So you have an expression here, and this, and then you have a list of expressions. So it's essentially like this is being bound to this. But I don't really want it like that. In a struct literal, all I need is just type. And then it would be nice if I could just get the type T immediately. Right? It'd be nice if I could get it immediately, instead of just getting a expr symbol. It would be nice if I can get the type T immediately. So what I did was essentially I just piggybacked off the parsing identifier function, and all it does is it just parses imports. So let's say import math, and then you have an identifier math dot something. It'll treat this whole thing like its own identifier. So this is where this is done here. So p import identifier, it checks, it resolves a symbol. Now, if p.token.kind equals toc, open curly braces. So let's say you parsed main.foo, and then the thing right after the identifier is this brace. Goto struct. So I like using gotos only for forward jumping and flattening all this nesting. So gotos are useful in certain situations. I use them all around this compiler. And essentially, you parse the identifier, and if you spot a curly brace right after, it's a struct initialization. And you can see that down here. So this parses imports, and then here, this resolves a table with the current mod and the literal. So this is the case where it would just be a singular, like main. And it'll jump all the way down here to basically this, the struct. And then it'll just create a new type using this symbol, and done. No need to go back and do backtracking with the expressions and trying to find out, is this a correct expression? Is this a correct symbol? Now, it's very simplified. So it's good. I like simplifying things in the compiler. Makes things a lot easier. Though, let me write a note real quick, because something just popped up in my head. Ambig with yeah, I'm depending on whitespace more and more. So, and then one of the most important things that I did, one of the most important things, was this. All the way up here. Just copy this, bring it all the way down. So, I implemented methods. Methods in this language, it's not, essentially methods are bound to types, and they can be invoked on that specific type. They can be static, and they can be not static. So let's say you have, see this one, foo.incr, just increment. It takes in the first argument, which is the self. So I don't like in languages where they force in methods the first argument to be named self. I don't like that, especially when a better name could be used other than self. Self is a pretty good name though, because it just lets you know that it's self. But this is a common idiom that I use in like V and things like that, where I just like to name the receiver just a single letter variable. That's how it really is commonly. So foo.incr takes in an A, which is foo, B I32, C I32 returns B. Void just takes in self, returns that. Static doesn't take in itself, which means it can only be invoked like this. It cannot be invoked like this. So, I mean, if you look at these, a.incr, you're just taking a field access, 20, 50. Foo.incr, this is just literally the literal. Not literal, it's just, you're just accessing the function. And then you call a, 20, 50. And then here, voider. Yeah, so you can essentially call it with the fully qualified or static syntax, where you just pick out the function itself. Or you can call it with a field access, which I prefer that way. Field access is good. So when you compile it, what comes out is very similar. So what's my compile command now? It is just this. Unknown type foo. Oh wait, hold on. There we are. Let's get foo. Good. All right, run it. All right, so this is a little huge, but I'll tell you what's going on. So, this is by first parsing. The main, so foo.incr essentially compiles down to its fully qualified symbol, which is this. So, foo is main.foo. Okay. Foo is main.foo. This is basically its fully qualified thing. This file is in the main module. And its method is main.foo :incr. Yep. There's a reason why it's not dot. If it was dot, it would be ambiguous because further modules in, they could share the same name. To make it not ambiguous, it uses a colon. Now this is its qualified name, and this is what will be generated in the binary. This is what will be generated as the output. Yeah, so you can see it here at the very top. Parsing HIR reorder. So this is essentially what gets thrown out from the parser. And main.foo :incr, and this is the function. Void this thing. Static does not take a single argument of main foo. Yeah, and you can see here in the original in the call, it's just these things. So when it gets parsed, it gets turned into field accesses and field accesses. And typing, oh wow, I have a lot of debug stuff. After typing, these field accesses here, a_0.void, gets turned into main.foo :void. So these all compile down to the exact same thing. You can see double, 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 and single. All right, so that's field accesses. One of the most important things I really needed to get done. All right, what else? Normalizing globals wasn't really much. Function type syntax, I can go over that real quick. Essentially, function types in this language, they used to be in a carried representation, which was just I32, I32, I32 all the way down. And then to get void, you'd have to go this to that. Now what I did now was there is no forcing of unary functions. You can have nullary functions now. And what I mean by nullary, I mean in this language, let's say something's like that, right? And the equivalent Rust function would be this to this. But really, I don't really want to accept an argument of nothing. I just want to have no argument. So this is a unary function, and this is a nullary function. So how do you represent a nullary function with this curried Haskell-like syntax? You can't. How I represent it in this language, though, is just this to this. And this is an argument list. This is not a tuple. This is an argument list. So you can have an I32, I32. These are arguments. And then this is the return value. The good thing about this is that you can emulate this curried sort of thing by doing something like that, or like I32. It's all very similar, but we're extracting. We're not going to get the overhead of curried lambda calculus sort of these function types. It'll all end up in argument 0, argument 1, return value, and that's the way I like those types. It's really simple. All right, brace blocks. So brace blocks are something. It's just this. It's just main main brace, and you can either have this to something, or if you force it to be empty tuple, force it to be void, you can just do this. Done. It's forced void. And this kind of syntax was in my first iteration of this language a year ago, maybe even 2 years ago. I really liked this kind of syntax, but at least I can bring it I can use this syntax now. So this is equivalent to this main here. This is functionally equivalent to this. Equals. Yeah, so this is functionally equivalent to that. So the brace, I call them like brace blocks or block expressions. I don't know. They're essentially equivalent to do as well. So if you use a brace in this thing, in the internal representation of the compiler, it will be a do block. You run it. Yep. See, HIR, or I mean even here, right? I think it's here. Yeah, it's just void empty tuple. If you put something inside though, let a equals 20. Run it again. Yeah, so it's just void do let a underscore 0 equals 20. Bye. Hey, welcome back. All right. I think that's basically what I did here. Sanity checks, errors. So I think that's basically all I did in between last stream and now. So I'll just repeat what I did. Incremental makefile, unified function call syntax. So I implemented methods. I re-implemented the address of. So address of works now. It just didn't work before. Yep, eager struct literal parsing. That works better. I merged the two type worlds together. So essentially, a lot of simplifications in the compiler. Not really much in the language. I mean, these brace blocks are nice, and method calls are nice. But mostly what I did between then and now was a lot of just simplification, really, in the compiler itself, which is really what I live for. Simplifying the compiler makes everything easier. So, what are we going to do this stream? So, we're going to do this. Constant evaluation. So, let me just create a global right here. Just name it global. And then we'll just call it, I don't know, 50. And we'll do this, create new. Okay, it could probably be more complex. I think we'll do like Fibonacci or something. Is there like a, I'll do factorial. Is there a fact iteration? Yeah, fact iterable. All right. Okay, this is in the old syntax as well. I swear I have a better fact iter. Good. So we'll take this function right here, and we'll essentially just extract it out to a variable, to a global. Factorial equals do, and then I. We'll just do let I equals. No, that's a huge. That's gonna be a huge number. 6. What's 6 factorial? Factorial. I don't know. Is it math? Fact. Yeah, I'm used to V where math is already important. Fact 6. Okay, 720. So, if you look at this, essentially it's just a loop with these things. So you can define variables inside globals. It's much like Rust. All right, let me add braces on these things. So, does that look much nicer? So, let's compile it. What does it do? Cannot mutate immutable variable. Okay, well, I'll just make it immutable. So, alright, so this is what comes out of the parser. It's essentially let I, let f, let take 2, go to a loop, a do, all of this stuff's in the middle. You do a break out of the loop, I minus minus, and then just return the variable at the last. So after typing, it inserts explicit breaks. So it inserts a break at take 2. This is like to break out of the factorial function. And inserts, explicit breaks, break with empty tuple. And then after normalisation. Normalisation is a very important pass that simplifies the AST or HIR into something a lot simpler, where I could run over, do static analysis. I could generate C. I could do interpretation on it. So normalisation is very important. And after normalisation, you can look. The loop block is completely gone. And then here, so there's no lets, I underscore 0 equals 6, f underscore 1 equals 1. The loop block is gone, it's replaced with a do with a repeat. Yeah, so if I is less than 1, take 2. Yep, so I'm doing forwarding. So instead of brkf, it essentially does this instead. Take equals f, brk nothing. That's the equivalent. So this is result forwarding that I explained before. And here, f, you're just multiplying. Let's go 3, I, yeah, so, and then rep 1. And then return take 2. So, I'll go over how globals are normalized. So I've talked about normalization before on my last streams, but for globals, it's pretty simple. All right. N global. This is the entry point for a normalization of global. So globals don't contain ret, only functions contain returns. Yep. So this is for constant evaluation after normalization. We'll have to add a ret to the end of the block. So I'm going to add a ret to the end of the block, and you can see after normalization it does. Yeah, you can see that ret underscore here, ret. So there's only one ret per global. And you can see list of statements, NHIR, expr target, putting the global IR description, list of statements. I'm putting in the HIR and then target return. So it'll just write the return value to just return. Yeah, and then global description, HIR expr T, expr do block, type bottom. Good, it just creates a do block. So, I mean, how could we do performant interpretation? So, so this is essentially after normalization, before normalization, we have a big tree, and this is basically a really functional language where ifs and control flows are expressions, and things like there's like lets and things like that. After normalization, it flattens everything down into a representation kind of like C. So loops aren't loops, if statements, do blocks. They don't return expressions. They write to intermediary values, and things like that. So that makes interpretation really simple. It's just going down on a flattened AST sort of thing. It's not like a control flow graph. It's a little bit more than that. Think of it more like a zig IR. Not really, but it's a lot simpler. Though what we'll need to do is a tree walk interpreter is really easy. We could do a tree walk interpreter, but we'll need to store like locals and things like that. And what I was planning is something wildly unsafe. But who cares? I wouldn't mind trying it. So I'll talk about what I'm gonna try. So this is the struct global T. This represents a global. It contains the IR description, type, location, and if it's immutable or not. If it's immutable. So the IR underscore description T is pretty important. So all it does is store list of locals and the root of the expression tree. And we run parsers on this. We run parsers on the root of the expression tree. We add locals, we remove locals, things like that. Okay, so let's go to locals. Okay, local mut, local immutable, local underscore ZST deleted. Alright, so yeah, assign multiple times, assigns once, and all flows of control. Okay, so this is type underscore T. This is basically a type, and then type lock. Yeah, so this is a local. So I'm going to go over how I really want to represent locals in the interpreter. Let's say you just have let A equals false, let B equals 50. And then, so essentially we'll have a list of locals. We have an I32 and a bool. Now, let's take the size of these. The size, I32 is 4 and bool is 1. So what we could do is just malloc 5, and then let's say we're accessing local 0. And this will give us an index of, so these are the size ofs, but the indices are these. These are the indices. So we'll access local 0. This is index into memory of 0. We'll access local 4. This is index into memory. Local 1. This is index into memory of 4. So these are memory offsets. So I don't know how wildly unsafe this is. I think this is pretty safe because we perform type checking. I don't think there's much of an issue for initialized values. We can just force everything to. We can just perform a mem set. Yeah, you'll eventually see on this is quite a simple concept. Instead of storing tagged unions where a variable can be anything, since we know the type already, we can allocate up front, and that's what I'm planning to do. So before we get to that, we have to just define our tree walk interpreter. So let's just start. Let's start by creating a new file. I don't know what I'm gonna call it though. Probably just HIR eval. Oh, whoops. Oh, no. Yeah, HIR eval. HIR eval.c. Okay, so include all.h and well, I don't think we'll have to make this be called. Yeah, I'll show where the interpreter gets invoked. Let's say you have a global. Yeah. Global 0 equals 0. Global 1 equals global 0. So essentially, the path that, after reordering, the path that the parsers will take, it'll go over global 0, and then it will go over global 1. So after it's finished global 0, it will perform interpretation, and then it'll just store like global 0 as value of 0. And then after global 1, it will perform interpretation, and then it will substitute value 0 in. So after we perform normalisation, we're probably going to have to invoke the evaluator, the constant evaluator. So, we're going to have to find the return location as well. All right, so let's begin something here. So I'm basically figuring this out as I go along. Yeah, we'll call this eval. So there will only be one point of eval, which is just root. You just call it on a root. So static void e global. Let me just name it like e. Yeah, e global. I want to only constant evaluate globals, and I'll expand it later. So should run up the normalization, and we'll probably raise an error if we can't. All right, then we'll create another function called ehir expr eval, and we'll take in and it'll have to return something. I wonder, since all types are concrete, there is no kind of dynamicism. There is no dynamic anything. Let's say you have let k equals I32 and that equals 0. Let c equals, let's make a bigger type. We'll do this u8 and then I32 equals k. I mean, essentially what happens after type checking, this k stays the same, but c is going to force cast it to a u8. So there's explicit boundaries on when things change type. So I could probably define like a struct that stores all possible kinds of things. It'll have to be heap allocated. It'll have to be heap allocated. So we'll do like some kind of like tagged memory representation. So we'll just like struct eval result t. Yeah, this is all wildly unsafe, but it seems fine for our purposes. Type definite. Yeah, so eval, just write e result t, it's probably easier. Eval result. So, it'll probably have to be, because we're going to be reinterpreting a lot of memory. So it'll be a type t, type. I don't even know if we'll even have that. I don't even think it will even have the type. I think it'll just be a union. And then we'll just get all the types. Where are those defined? Just here, right? Right. There we are. So we'll just go d underscore that. Right. And what do we not have? I size. I don't know what I size is defined as. I know what U size is. It's size t. Yeah. PTR diff. And size t. Size t is one of them. Okay. And then what else? There's definitely more. There's definitely more. We'll have to do something like greater than or pointer, probably or pointer. Pointed away. Pointer. I think we're gonna name it like a D. D large. So this is greater than 8. Greater than 8 in size. Or probably not non-concrete type. Because these are all concrete types. So I'm probably gonna leave this out. I'm probably gonna have to do this off stream because there's gonna be quite a lot of theory I'm gonna have to figure out. So this is just our result. Essentially, it's just a big union, and we can return it. All right, NEHIR expression eval. It takes in a IR desc t, so description, but we'll probably have to define our own kind of descriptor. Here, we'll do this. Struct desc t is our own descriptor for the context of the interpretation. It'll store the current IR desk, and it'll also store a list of locals. So this will be basically constant time. So if you're accessing a local, it'll access into this list of things and get its type. So we'll have basically a stack, which is just a char pointer, really. And we'll get a list of, so it'll be U16's U32 size. So it'll be an array of offsets. Local offsets. Yeah, this is pretty interesting. We'll take in a edesk. So let's construct a edesk right now. So we'll need to store all the locals somewhere. It's desk equals global desk. And the stack. So we'll essentially need to construct, we'll have to run over all the locals and record their offsets by taking a size off. Whoops. So we'll go over 4 U32 equals 0. C equals global dot, here, we'll save this up. We'll go desk.desk, which is basically desk.desk, locals. So this is the list of all the locals. I is less than C, I plus plus. And then we'll store a U32 C offset. This is the current offset. And then we'll get a U32 size to 0. We'll have to make sure, we'll have to worry about alignment as well. That's important. That's really important. We'll have to get so we right now we have type size off. Type size off. All right, and then we have to probably make a type alignment. The last time I did this was when I was working on the WebAssembly backend. If I get stuck, I'm gonna have to open the code base because I'm pretty familiar with that. Okay, so let's just do type align. We'll get the alignment. Most of these alignments, here, I'll just delete this. Most of these alignments are really simple. Yeah, I size is aligned to pointer. I don't know if it is. I don't know if it is. I don't know if the alignments are right. Let me do something real quick. Okay. Let me search for alignments of size t. I don't know if there's any kind of, I think it's either like, if it's the size of, stood size t. Alignment? No, this is an ABI thing, so I don't know why I'm looking at CPP reference. Let's go Godbob. Alright. Yep. Just create a const int test equals size of. Gets to def size t. Okay, we know what size, it's 8. Where's a how do you get the alignment? Align off. Okay. Thanks, C11. 8. Okay, so this is gonna be my where I'm looking at. So and also there's specific alignment if we're on 32-bit as well. For example, an F64 is aligned as 4 on 32-bit systems, so I'm gonna write it to you. So yeah, we'll get type kind of top. Yeah, so this is basically the alignment of all of these. There's no other kinds of alignment really. We'll raise an error for these though. We're basically invalid types. We're gonna do this. Yep, and the default's something separate. Okay, so these are the alignments. Now, I don't remember how you round up to a multiple of the alignment. I'm gonna have to bring up the WebAssembly backend, because I remember writing code for that specific thing. Alright, so we're gonna get some V action. And serialize, right? Serialize. There we are. Here it is. Code bird from native. Yep. Thanks, spydr. This is your code, by the way. All right. So we've struct info. So let's get the alignment of its size, total. Size equals. Let's get the current local. So local t pointer to the local. Desk locals I. Like a ref to that. Local. So we'll go. So we have. I'm gonna make this public. You know what's the most annoying thing? Just copying a function and then just going into the header, just finding where to place it, and then just pasting it. It's annoying. It's one of the most annoying things. Alignment rows. This is why, like, as soon as I can get one of my best luxuries would be writing in a new language and not having to deal with header files. Also, the rows for ZSTs, zero size types. Okay, so we got the type align. Actually, I want to rename this align of. That's better, align of. Alright, so we'll get the size. So we do a type size of align, do a type align of. Okay. So 4 fields, we get the size and alignment. If size equals 0, offsets to 0. We're gonna need to assert that size. What is it? Assert size. It's not equal 0. Yeah, it'll never equal 0, but sometimes it will, because locals that are deleted will get the name of underscore local zst deleted, which means there is zero size type, and the local doesn't exist anymore after normalization. So we're gonna have to do this. If local dot kind equals zst deleted, we'll have to we need an array of offsets. So offset is null, and then we'll just do an push offsets. Not zero, but the current offset, and then continue. Or possibly even just -1, because I want it to throw. I want it to segfault. Alright, then continue. Okay, so we know the size is not equal negative, it's not equal 0, but type size off. Alright, so we need to calculate padding, so this is the current size. Size right now equals 0. Actually, no, there's a plus. There's a plus there. Okay, so total size. So padding equals field alignment. So align minus total size. F align. What's the F align? Yep, align again. Align. There's 3 mentions of alignment. I think I don't know. I have to look how this is implemented. Push offsets size plus padding. No, it's total size. And total size plus equals size plus padding. If field alignment, is field alignment. Oh yeah, this is just total alignment. There is no total alignment needed for this. Okay, and then the size will need to be a multiple of the alignment. We can just round it up to 8. We can call it with malloc, and malloc will automatically round it for us. Okay, well we can just malloc desk dot stack equals malloc total size desk dot offsets equals offset. All right, let's just print these just in case. Here, instead of I'll just do that instead. Okay, good. All right, we'll print all the offsets. So for U32, I equals 0, C equals R len U, desk equal offsets. Let's see. Okay, and we'll just print them. Print U. Now we'll go by locals as well, because this is the size of all the locals. So we'll just print local. SV from desk locals. And then okay. And then we'll just print the whole size off. So just print size equals okay, well let's see. Let's see what it does. We'll put a assert not reached. Make it raise an error, and then we'll run it. Okay, well it never gets called, so we'll have to call it. Yeah. HIR eval global. put this in all. Actually, we need to put this inside normalization. So after normalization, we'll just call this. For now, because I'm lazy, I'm just going to put an extern and define it in here. That's why. Global. Okay. So this gets put in here. Eval. So we have IF. Oh, wait, is this? I_none. Where's this from? Okay. Some locals don't have names. That's one of the important parts. Cool. I did not know you could do external declarations and functions in C. Yeah, yeah, you can. You can even drop the extern. It's implied. You can define structs inside functions as well. Okay, where's the error coming from? Oh wait, if name equals. Right. And down here. So let's see. We have IF take and a intermediary local. I don't know what that intermediary local's for. It's for something. Oh, for the I minus minus. Okay, so we have size I32. So that's we'll put the we'll write down the type as well. %s. Just the desk. I'll wrap this out into a local. All right, so we have basically 4 I32s. We have an I32, 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 I32. I don't know why this should start at 0. I don't know why it's not starting at 0. Total size plus padding. Now let me take a look at the code inside. Struct offsets. It should start at 0, should it? So F align. So this is the field alignment minus total size, field alignment, and field alignment. Just padding. Field size plus padding. Yeah, I don't know why it's not starting at 0. Or maybe this, you have... Oh my god. Thank you. Thank you for spotting that. Thank you so much. So does it start at 0? Yes, it does start at 0 now. Okay, so we have 0, 4, 8, 12, 16. The size, well, yeah, the size should be 16. Well, good. Now we have basically our stack, which is just, we'll have to, I want a malloc. Not malloc, I want to, this is the first time I'll probably use calloc ever. Yeah, calloc. Actually, no, I'll just memset. Desk stack 0 total size. Actually, we'll do OXCC because that's basically the industry standard for uninitialized. Oh, we'll probably you know what we really need? We probably need like tag bits to check if this is uninitialized memory or not. Yeah, calloc. It's just for arrays, but I deal with bytes anyway. Okay, so this is wildly unsafe. I want to throw an error at runtime. I want to throw an error at evaluation time when we access an uninitialized value. So what we need to do is we need basically like tag bits. So I think it's fine if we just here I'll explain what I mean. So let's say we have basically going back to this example, we have two locals, I have to do two in a bool. Local 0 equals 0 and 1 is 4. We'll go tag bits. We'll just like uninit 0 false 1 true. So basically I just want to store an array of bools to see if they're initialized or not. Just an array of bools. So let's do that because I want this to be at least a little bit more safer than runtime, at least before I get static initialization in. Not static initialization, static analysis in. So let's just create let's do bool local tag. Let's just name it tag, and we'll malloc a list of tags. Local tags. We'll malloc the size of locals, so we'll just abstract that to a variable. Actually, yeah, I will. Locals. Yeah, this list of local offsets. Well, they're the same size anyway, so it doesn't matter. Let's see. Okay, so we'll malloc the amount of locals. So one bool for each local, and we'll initialize them to. So this is basically init. Initialize them to false, which means uninit. And we'll raise an error if we try and read initialized memory. So, desk dot local tags. And what we should do is probably comment that out since we already have checks anyway. One bool for each local. So this is just the uninit setting. So when we get into evaluation, everything will be basically initialized to 0. Here we'll go. We'll write like init or not. Actually, we skip if there are ZST deleted. Okay, I'll do a to-do. May store ZSTs. Actually, that's something I shouldn't be worried about. Okay, so yep, desk local tag. So we'll see. They're all not in it at all. Oh, what's this? Loaded value 190. Oh, okay. This is undef, undefined. I wrote N0. What am I doing? Okay, so that is definitely uninitialized memory. Okay, so yeah. Good thing I have a msan memory sanitizer. Okay, so let's go and evaluate basically the whole thing. Eval desk, and we'll put in the. We'll extract this out to a function, just called like a state. State. All right. This is the current state. Call eState with desk, and we'll call it after. Is it desk pointer? Yeah, desk pointer. Yeah. And we're taking a HIR, expr, T, expr. It's desk, HIR. Okay. So, we'll have to go one by one. We'll do a big switch, basically a big switch on expr.kind. And we'll just take all of the stuff in here. Let's go one by one. So we need integer literal. So let's just run it and see what happens. Okay, unreachable. Okay, so let's just comment it out, this thing right here. Let's go factorial, this number, global equals 20. Alright, so this is purple now, but the error comes from, yeah, we'll name it, we'll make a variable, that a equals 30, return a. Let's see, so yeah, single init equals 0. So, integer literal. We'll have to switch on the type, too. Let's check these things. Assert type integer. I assume this should be true, but let's just write it here just because. And then we will switch on the type. Yeah, i8, isize, u8, or we only need a couple of these anyway. Switch, expr.type. Alright, so bool's going, f32, f64 is going. Okay, so we have all of our integer types. And we'll just construct them as such. So we need result. R for results, and we'll just do assign d di8 equals. We need to do parsing as well. Stir to. I'm just gonna take this. Yeah, I don't do any kind of integer bounds checking. I probably should, but I can leave that for a while. No, not really for a while, but just enough. So I have the v basically, and you know what I could do? I could just write it. Like, now, how could I could probably do it this way. I could take this, and then go r.d. Let's go this. Do that. This lowercase. rd. Let's go this equals v. Right. Very good. Multi-cursor. All right, and then just return r. All right, what's the next one? Do a print. We'll extract the kind so we can make sure it's kind 5. one's number 5. Oh, do block. What is the do block? Okay, we'll need to extract everything to this essentially. So all of these can go. All of these can go. Make this default. Alright, we do this in 2 ways. We have EHIR expression eval, and we have to do EHIR stmts, stimulants, eval. I'll take a list of expressions. Assert. Yeah, so after normalization, every single list of statements are basically do blocks. Yeah. So desk. EHIR stmt's eval. So we'll get the HIR, the do block expressions. Now let's go over the statements. So for loop. Essentially what I want to get done this stream is not much. I want to get done essentially just a simple example. I won't get done the factorial example. Maybe even just this example and then a little further on. It's just because interpretation is pretty complex. I didn't really give it much thought before I started the stream. So EHIR. Interesting. Eval. Desk. Expr. Okay, that's it. We'll do a switch on all of the possible statements because there are a notion of statements after bringing everything down from expressions to normalized form. So we have case expr break. We'll have a break out of the loop. It's just a return. Case expr assign. That's one of the important things we need to do. So we'll assert not reach that. That's another statement. All right. Okay, expr assign is the most important thing. So what we'll need to do, is, so stmt d assign. It has a LHS and RHS, so we'll get the RHS and we'll evaluate. So EHIR expr eval desk and right hand side, the E result. And then what's after basically is an assignment. So we'll just do asserts for now. We're not going to write to any globals. Well, we can't write to any globals inside a global, so that should be checked as well. So we're going to assert. Yeah, so in a global initializer, you can't write to globals. That's not allowed. HS kind equals expr local, and then we'll just extract the local. So we'll go r local p local equals stmt d assign LHS d local. This is our local. And then we'll essentially write to it. And the type checker, we can assume that these are the right types, so we can just go down and assign them. So EHIR, we have to go to desk. So we'll first we'll first set local tags. Local equals true. Definitely init. Desk local offsets. Local. This is a char pointer. No, this is offsets. Okay, we'll get a U32. Okay, and then what we'll need to do is do some pointer magic. This is so unsafe. This assumes that the compiler's ABI is the exact same ABI as a compilation target. Wait, no. This is perfectly safe. This is perfectly safe. Because whatever you compiled the compiler for, that's the ABI that it's going to do constant evaluation. So this seems fine. This seems fine. We'll have to make sure this is host ABI though. To do host ABI, not target ABI. Okay, these are important things you need to remember. So desk stack plus offset. This is basically our void pointer. Lock. And we'll basically have to cast to this. So this will be our void pointer. We'll have to cast it to a resulty. I'll have to check with the standard to make sure this is okay, because I hope it's okay. Get our result, and we'll go lock equals res. All right. Maybe. Thanks, Asan. So what's the error? Heap buffer overflow. Desk stack plus offset. So we'll do a print. Read. I'll take a read at offset. I just want to see what that offset is. Read it, read 0. So it's read, and then we'll do key. Okay, so that's basically the offset. So heap buffer overflow. This happens right here. So desk. So I'm reading the stack, which is char pointer plus offset. According to that. Just started implementing IR and normalisation for cspydr to make the backend simpler, because I definitely want to support platforms other than x86 Linux. Yeah, normalisation is probably one of the most important things in this language compiler. It's if you want to talk more about it after stream, I can help you. It's really important. So the language that I have right now, it's just this functional thing where control for if statements, loops, do blocks, they're all expressions. After normalization, you're essentially flattening everything down into basically like a flattened imperative C-like representation. So instead of assignments being expressions, they're now statements. They're flattening them all down. I have a very nice algorithm, the way I've written it out. If you can look at the code, it's very simple. It's very simple. It's only got a couple principles, like 2. Yeah. So this is if Spy's watching, just like Spy, how Spyder said, doing it all in the ASM backend, V could benefit so much from a normalization pass. Just normalizing the V syntax AST itself will make all the backends. It'll make the backends much easier to implement. See, passing V's AST straight to the backend, like how rich it is in its expressions and things like that. It is just so complex. It is, yeah, Spyder, yeah. In the WebAssembly backend, I mean, it's just crazy the amount of hoops I had to jump through, and intermediate values. There's, I mean, if you look at cgen, I mean, just look at cgen. Look at the look at the struct. Look at this struct. And imagine duplicating that over the parser, the checker, the transformer, and then cgen. I don't know. It's I have high hopes for V when it goes on. When things get better. But, yeah, it is crazy. Okay, well. It should be better with Joe's rerat though. Yes, yes. That's right. So heap buffer overflow. Located 0 bytes after a 4-byte region. I don't know how that's happening. What's the total size? %d is total size. Total size is 4. So I'm allocating 4. So I'm gonna have to write the equivalent of a size of 4. So e result t is basically as big as 8 bytes, but I'm trying to write to a size of 4. Okay, thank you, msan. This is, yeah. So I'm gonna have to go one by one. So I have to go. I have to create a function for this that unwraps it one by one. So static void EHIR write value, and then it'll take in a void pointer. And we'll take in a, what is it? E result. And then type T, type. And I'll just switch over all the types. Wonder if I could do this with macros. I don't know, probably not. Type. So I8, I16, I32, I64, isize, UAs, usize. I wonder how Rust does this sort of thing. So results. Name this R. Need to cast lock to a I8 and then perform that. So why is that? Why is it erroring? Cast to small in, oh, it has a pointer. Okay, now let's see if I can do this for all of these types. So I do it like this. Take this. Yeah, I love multi-cursor. Lock equals r dot the this. Okay, I don't have isize, but I do have ptr diff, and size t. All right. Yeah, so EHIR write value. This is just a proof of concept. So it's just desk plus stack offset, result, and deassign type. Okay, now, great. Now, where's this error coming from? This is probably coming from a read from a local. So let's do that now. Case expr local, and then we'll. You know what we should do? What would be easier? A mem set. Memset's much easier. Mem copy lock address of size. Wow, much simpler. And then we'll just do a static void EHIR read value. Easy. So when reading from this, we'll need to basically check, is this definitely initialized? Is this initialized to memory? So we'll just have to do this. If we'll go expr.d local. Alright, so we'll have to first assert so that desk local. Actually, we'll do an error. If desk local tags local. If not printf. We'll do a print air with pause. Yep, and then we'll do location. Alright, and then we'll grab the offset, and then we'll do a EHIR read value. E result. Just return at the end. Another annoying thing too is littering all my functions with static. Should really be static by default. Okay, read value. Okay, where's this from? So let's see, what do we really have? What kind is kind 22? HIR. So which one's 22? Return. Okay, return is when we basically leave from the whole thing. So we'll probably yeah, okay. Case expr return. We need to do res. Lock. So we'll need to create a return. So we'll do a e result t result. Result t result. Desk dot results equals results return. We'll have to do a set jump. We'll have to do a set jump. Jump buff. Jump buff wrap. So we'll do a if long jump. Yeah, I wish long jump was like built into C as like a language feature. That's what I want to do in my language. I want like an explicit rewind keyword, unwind keyword, set jump. Do an E state at the end. Yeah. Alright, so it seemed good. It seemed good. What we'll have to do is do a print. We'll have to be able to print these things. Okay, E result. R type G type. I mean, that seems about right. Is that right? Yeah, sure. Result equals. I don't know. It's desk dot. Yeah, that's global. Global dot type. All right. So this is where it's finished. It's finished. Result is 30. Okay, 35. Okay, 35. What's the time? Actually, 33. I think I should end it off now. Actually, we'll do addition. We'll do addition. So, case expr infix, because this is really quick. We'll do switch expr dot dinfix dot kind. We'll do a. What could infix be? Yeah, talk is infix, so it's usually. Yeah, I'll just take these. I'll just do talk add. I'll only implement add for now, and I can do the rest later. So switch. So not reached. Break. So. I wish that there'd be like a way easier way to do this, like generic rights instead of just doing all of that against all the concrete types. You can't do it any other way though. So we'll get E result of LHS and RHS. And expr.type. And just do a default. But the rest of it though. Yeah, I think I'm probably gonna get C code generation done before I have constant evaluation, because this is like the most tedious thing. Right, so over this lowercase copy LHS dot lowercase plus we'll go R dot this equals yeah, I'm gonna have to do I'm gonna have to do macros for this, which I'm fine with. But yeah, multi-curse is fine for now, and then we will just yeah, let me just return break. All right, so that works, and then we'll test its addition. So we'll do a plus 50. 35 plus 50, what is it? 85. Is that right? Yeah, that's right. That's right. Okay. And the end of that, init is 1. So let's try and read from an uninitialized value. Just before that. Let a is I32 and then a. What happens then? So use of uninitialized local. Perfect, because that is genuine uninitialized memory. Run it again. 85. So that's good for now. That's great. I think we did enough. We did enough, yeah. We'll go over here. I did normalization. We'll name this eval. Basic impl of global constant evaluation. Delete this set jump. I think that's it. Yeah. Okay, that's good enough. So I will add the hash in here. So this is hash stream 18. 16, 17, 18. 18th stream. Wow. 18 streams. Okay. Seeing changes, and that's it. So if anyone has to say anything, I think I might close this down in probably about 30 seconds. Just eval. Let's just copy all of this. So, that's it. I think I'm gonna end it here. So, good night, everyone. It's almost 12 for me. It's a good stream. Good stream. I worked on some good stuff. So, goodbye. Goodbye. Good night.